Part 2 of the gas laws practical is about Charles's law. So you'd like to have a setup that looks similar to this, where you've got a big beaker, you've got a thermometer, and you've got a ruler with something called capillary tube attached to it. We'll talk about that in more in a second. So capillary tube is designed to have a volume of gas or air at the bottom of it. It has a blob of sulfuric acid in it, which moves up and down according to whether the volume of the gas is expanding or contracting. Now, it's really important to note that this has an open end. We'll come back to this later, but an open end ensures it's at atmospheric pressure. Otherwise, if it was closed, the pressure could change inside it because it's kind of closed off from the surroundings. So the purpose of this practical is to prove Charles's law, which is that the volume of a gas is directly proportional to temperature at a constant pressure. We're also going to use it to work out a value for absolute zero. So let's have a look at the method for this practical. We're going to look at the method first, then the graph, then the calculation to work out absolute zero. So the first thing to do is to boil a kettle and carefully add hot water to the beaker, and it's got to be high enough to cover the air sample. So to cover basically the sulfuric acid as well as the air sample. It's really important to allow temperature reading to stabilize to make sure you're not recording the temperature too soon before the water's heated the thermometer up to appropriate level. Then you're going to record the temperature and the length reading. Next, and this does take a bit of time, you're going to allow the water to cool very slowly, and you're going to try and stir it as regularly as you can and record the temperature and the length readings about every 5 degrees as it cools down. It's important not to do this all at once because otherwise it won't happen evenly. If you were just to add loads of cold water to it, that would mean that some bits will get cooled and other you'd have to stir it. You might miss the 5-degree mark, which would be a big problem. Now those until about 20 degrees, if you have time to go to room temperature, are about all the measurements you need to take. So let's talk about first of all, why are we not measuring the volume? Why are we measuring the length? So in this tube, the length is the height of the air bubble we've got below the sulfuric acid. The reason we don't worry about the volume is because the cross-sectional area is constant. So capillary tube has a very small cross-sectional area and it's constant throughout. So the first thing is to ensure water cools slowly, as we mentioned before. So make sure the thermometer and the air inside the capillary tube and the water are all at the same temperature. We can make sure the water covers the air. We're also going to measure at eye level to avoid parallax error, especially when you're measuring, in particular, the length, because it's not going to change by that much, but the length or the height inside there could change depending if you're at eye level or not. Next, let's talk about safety. So the safety in this practical, we're going to make sure we wear goggles because there is sulfuric acid, which can be dangerous to the eyes. And obviously we're dealing with boiling water. You don't need a funnel because the beaker is quite big, but just pour it slowly and in the middle of a table so it doesn't splash all over people standing around the table. So what about the results we're expecting from this practical? We're expecting to find the two things are directly proportional, length and temperature. However, units are really important here. For once, we're not going to use Kelvin, we're going to use degrees Celsius on our x-axis. And the length, it doesn't actually matter the units, you could use centimeters or millimeters, depending on what your ruler is measured in, as long as you're consistent throughout. So when we're writing down our results, plotting our graph, we should find that they form a roughly straight line. Obviously, you want to try and do repeats if you can. However, it's quite a long set of the practical, so you might not be able to. However, you should find that if you are measuring T in degrees and L, you should find it doesn't pass through the origin, which sounds a bit weird because we're taking up measurements up to 20 degrees and we haven't gone down to 0 degrees. If you draw the line all the way back to the y-axis, you should find that actually it's not going to hit the origin at all. Now, there is a reason for this. That doesn't mean it's wrong. This is because at 0 degrees, that's not the lowest the volume can get because we know we can get negative temperatures and that's how we're going to find absolute zero. So we're going to put our equation or our graph into the form y equals mx plus c. Our y-axis is the length, our x-axis is t, and we can find the gradient and the y-intercept and use it to find absolute zero. So c is our y-intercept, so let's find that first of all. So that's when the temperature would be 0 degrees Celsius, what would the length be? And the gradient we can calculate with a nice big triangle. So we're going to use these values and do a little bit of manipulation to this equation to find when L is 0, what is T? Because when L is 0, that means the volume is 0, that should be absolute 0, the temperature that occurs at. So at that point there, let's change our L equals mt plus c equation a bit. If we've got L is 0, then we're going to have 0 equals mt plus c. Rearranging this a little bit so we can make t the subject. So we should be left with t absolute 0 is equal to minus c over m, so the y-intercept divided by the gradient. So this is absolute 0, so t naught. All we need to do is to find the gradient and the y-intercept, and we should be able to find a value for absolute 0. So one thing to note here is that we shouldn't just put all our results and then extrapolate all the way back to absolute zero. This is a bad idea because your results will all be clustered around 20, 30, 40, 50 degrees. Absolute zero is about 5 times that away at minus 273. Your gradient is going to be really unreliable if you're doing this all by hand. So it's just not a good idea to do. You should do it mathematically instead. And hopefully you should get a value close to minus 273. However, there are some uncertainties to deal with. So if you don't get that close, you can blame that. Let's finally talk about the uncertainties with this practical, so Charles' law practical. So there is a calculation, so you're calculating absolute zero, so we should be able to quote that with an uncertainty to it. However, obviously we're using a graph, so we're going to look at how do you work out uncertainties when there's a graph involved. So the absolute uncertainty in L, the length, is likely to go up and down by 1 millimeter. Obviously, look at your readings themselves, but that should be the resolution. So that's going to be our uncertainty, is to look at either end of the tube, and that's going to be half a millimeter either end, meaning the whole thing is 1 millimeter absolute uncertainty. In a thermometer, again, it depends which thermometer you're using, we're going to consider it to be the resolution. So let's say it's plus or minus 1 degree. So when you plot your graph, and bear in mind this graph is important because we're using that gradient to calculate our absolute zero value, you could draw on error bars to represent these uncertainties. So let's say you've got the absolute uncertainty in L, that would be a vertical error bar, and the absolute uncertainty in T would be a horizontal error bar. The purpose of error bars is to show the uncertainty in a visual way, but also so you can draw in lines of worst fit. So we know about lines of best fit, that goes sort of between as many of your actual points as possible. The line of worst fit you draw that should go through or between all the error bars and will either be as steep as possible or as shallow as possible. It doesn't actually matter which, because if you take the shallowest one for this equation here, you just take the modulus of the final answer to get the percentage uncertainty. So the percentage uncertainty in the gradient is going to be the difference in gradient between your line of worst fit and your line of best fit. Then you divide that by the line of best fit. So it's the same as before. It's the uncertainty divided by the value and times by 100. So let's say you're working out absolute zero, which we are. So it's minus the gradient over the y-intercept. We also need to know the percentage uncertainty in the y-intercept. And yes, this is long, but it's worth it being thorough to make sure we know what uncertainty our actual value is given to. So if I've got another y-intercept, let's say from my line of worst fit, and I've exaggerated them here, there won't be that much different, but just so you can see, the percentage uncertainty in the y-intercept is the similar method as the gradient. You're going to take your line of worst fit y-intercept minus the line of best fit y-intercept and divide that by the line of best fit one, then times by 100 to get it as a percentage. So how do we combine those together then? So how we do it is because we have M over C, we have those two measurements. So we have to then work out the percentage uncertainty by adding the percentage uncertainty in the gradient plus the percentage uncertainty in the y-intercept. We add them together because even though they're divided in the equation, that's a general rule. If you're dividing two variables or two quantities to find the percentage uncertainty of the overall the overall t here, you have to add together both of them because you've got two different variables, two different quantities you're combining together. So your absolute uncertainty value should have a percentage uncertainty. You can then make that an absolute uncertainty because from experience with this practical, sometimes it doesn't end up being that close to minus 273, but hopefully it's within your uncertainty value. So there you go, that's Charles' Law Practical. I hope you found that useful. Please comment any questions you've got. Drop it a like if you found it useful. Have a look at some more A-level physics videos. But thanks very much, and I'll see you again soon.